three main components of machine learning that we have talked about the last 2 weeks? Data, model, and loss. Very good. First, data. So data is a set of small units of information, which we call data points. Each data point has properties, certain properties. Some of them we call features. Features are those properties we can measure easily. And then another type of property is some high-level fact or quantity of interest, which we call label. For example, one of my favorite examples now, very timely now also because we have snow. So a data point is some ski day, and the feature might be the morning temperature. We can measure this easily in the morning, but what we're interested in, the quantity of interest, is the maximum daytime temperature. So, and in order to learn a hypothesis, so machine learning is about learning a hypothesis that reads in the feature X and produces an estimate or a good approximation of the label. So in order to do this, we need several data points. So a data set or data is just more or several data points. And typically the more data points we have, the better. Yeah, one important parameter or key figure of a data set is the sample size, the number of data points, in particular, the number of data points for which we know the label. So if data is considered the fuel of machine learning, then it's the raw oil. And the labeled data points is then the high performance, high-end fuel that you use for your engines. So we would like to have labeled data points. The labeled data points are really this is the gold in the data. Yeah, here's one example with 4 data points. So these 4 data points are obtained, for example, by the Finnish Meteorological Institute. For each data point, we know the feature, the minimum temperature and the maximum temperature. So far, so good. So this is data. Yeah, what do we do with data? Data per se is useless. We always need some model or a hypothesis for the data or for the data generating process. So in this course, I mainly use the term hypothesis for a map, a function that reads in the feature as an argument X and outputs some number that we interpret or that we use as a prediction for the label. That's why we call it Y hat. So it's an estimate of the true label Y. Yeah, and machine learning only becomes interesting if we have more than one hypothesis, because if we only have one hypothesis, then we can only use it. And an example is this song identification app Shazam. I think now there's not much learning going on anymore in the Shazam app, or not continuously, but what you do on your app, you just run a function that reads in the features of a song in the case of Shazam. So it's called Shazam. And it outputs a guess for the song title. So the Shazam app mostly does nothing but evaluating a function, and this can already be challenging. So if there's a function is very complicated, then evaluating a function might already be a challenge. This is also called inference in machine learning. Whenever you hear machine learning inference, then this means just evaluate a hypothesis map in order to compute a prediction. This is inference. But what we in this course are mostly interested in is how do we learn a good hypothesis? And we, as I said, machine learning only makes sense if we have more than one hypothesis. Otherwise, there's nothing to learn. And one of the simplest spaces or hypothesis spaces or sets of such hypotheses is a linear function. Linear functions we have quite good grip on. We know more or less their properties, their statistical properties. So this is a good first choice, a linear function. But why not using degree 3 polynomials or degree 10 or degree 100 polynomials? So typically we have many different options for these hypothesis spaces or models, and each particular model corresponds to one machine learning method, like decision trees uses one particular hypothesis space, deep learning uses another construction of a hypothesis space, polynomial regression, another construction of a hypothesis space. So which one to use? And for this, we need validation. So let me explain what validation is. Oh, yeah, first of all, if we for some reason we know what a good model is, or we know what a good hypothesis space is, then first we have to measure the quality of a hypothesis within a hypothesis space. And for this, we need a loss function. So a loss function is a measure, in some sense, a measure stick or a scale that tells us how good is one particular hypothesis. And some popular loss functions are discussed in my lecture notes. For example, the squared error loss. So for each data point, we compute the predicted out, or the predicted label. So it's this here for this data point. This is the predicted label, but the true label is here on the y-axis. So there's a difference. This is a prediction error. And the squared error loss uses the square of this prediction error to measure the quality of a hypothesis. So, and what machine learning or many machine learning methods do is then solve an optimization problem. They solve the optimization problem of finding the hypothesis out of the hypothesis space, which has the smallest average loss on the training set. This average loss on the training set we also call training error. Okay, and then what happens nowadays, because we have so powerful hypothesis spaces, we have such large hypothesis spaces like artificial neural networks. They involve billions of parameters, and these artificial neural networks, or these deep networks, they represent extremely high dimensional hypothesis spaces. But you don't need to look to deep learning. You also see this effect for polynomial regression. So if we use as hypothesis polynomials, and if we allow for a very large degree, then it turns out when you have a very large hypothesis space, you can easily fit perfectly fit the training data. So it's not really a challenge to make the training error small. So for example, for a linear predictor, we get some large training error. So here we see with this linear curve, no matter how we position it, we will incur some error, some significant error. However, when we look already at degree 3 polynomials, then we almost perfectly can fit these data points. So we get training error close to 0. So if we use larger degrees, we get the training error pretty soon towards 0. And this is not what we want. So because overfitting might happen. Overfitting means that we overfit the training data. So we focus too much on fitting the training data, which we can do easily just by, in some sense, by memorizing the training data. We just pick a function that perfectly goes through the training data. And if we use a large enough hypothesis space, we will for sure find such a function, because there are simply so many functions in a big hypothesis space that just by pure luck, we will find one that perfectly goes through the training data points. But such a function might not be any good on a new data point. And this is what we really care about. We don't care about how good is the predictor on the training set. We care about how good is the predictor on a new data point. For example, when the predictor is used to predict the maximum daytime temperature, then I don't care how good it is on old FMI data, but I care how good is this predictor today. This is the new data point. And here, if we overfit, then this predictor might not be any good on other data, which is different from the training data. So this is referred to as overfitting. And this is one of the key challenges in machine learning, to not get yourself fooled by overfitting. So whenever you start applying machine learning and you choose a model like polynomial regression and you train it on some training data and you get the training error 0, so this is just a good warm-up exercise, but it doesn't mean much. You always have to try out your predictor on data points which are different from your training data set. And this is exactly what is validation. So validation means try out the hypothesis that you learned on a training set on some other data points which are different from the training set. Yeah. Just before I talk more about validation, you can easily show using elementary calculus knowledge that, for example, if you have m data points, like if you have 2 data points, m equal 2, if you use a degree a polynomial with maximum degree n-1, you can perfectly fit any m data points using such a polynomial as soon as n is not smaller than m. So, and this tells you that in order to avoid overfitting or to get any meaningful result using polynomials of degree n-1, you need to use at least n training data points. So this m is the size of your training set. And you want to avoid this condition, because under this condition, you can perfectly fit any training data set. And this means you will overfit. So in order to avoid this bad condition, you must make the sample size sufficiently large. So you must, if you have a degree of 100, or n-1 is 99, so this means you need to have at least 100 data points to reliably train a polynomial regression method. And in practice, it's even better to have 10 times more. So to be 10 times, to be away from this condition by a factor 10. So if you use degree 100, then it would be good to have 1,000 data points. And this n, which could be interpreted as the number of equivalent features of a data point used by a linear regression model, this n might be billions for modern machine learning methods. Like this n might represent the number of tunable weights in a deep neural network, and they have billions of tunable weights. So this condition here tells you that if you use one of these super powerful deep neural networks, you need to have 10 times more than billions of training data points. For example, if you want to use deep learning to detect if an image shows a cat or not, then you need 10 times more than billions of images for which you know if there's a cat or not. Okay, yeah, here, this is an illustration of this condition. So if you have n equal 2, which means maximum polynomial degree 1, and 2 data points, then for any, so each color corresponds to one particular data set. So here's one data set of 2 data points. Here's another data set of 2 data points. Here's yet another data set of 2 data points. And for any such data set of m equal 2 data points, you will always find a hypothesis that perfectly goes through it, passes through it, and makes 0 training error. Okay, so the big idea now is to do validation. And how do we do validation? Well, we split the data points that we have. So in this case, we have 4 data points. For example, 4 previous days that we download from the Finnish Meteorological Institute. And then what we do is we split it into a training set and a validation set. We use the training set to learn the hypothesis, for example, by minimizing the average squared error. And then after we learn the hypothesis on the training set, we just apply it on the validation set and diagnose the method. So here I have illustrated a simple example by using a linear hypothesis. So we use the errors, these errors we use to optimize the weights of this linear predictor, like the offset or the slope. This is tuned using this data set here, this training data set. And then after we train, we are finished with the training, we try it out on the validation set. And then looking at the validation set often allows us to identify overfitting. So for example here, like this degree 3 polynomial, which I showed before, perfectly fits the training data, but we immediately see that it overfits because the validation error is large. Yeah, so this is maybe the most important picture for the practice of machine learning. So you have 2 bars or some visualizations of 2 quantities, the training error and the validation error. And you diagnose machine learning in 90% of the time when you do machine learning in practice consists of comparing training with validation error, and based on this comparison, decide what to do. Should you collect more training data? Should you use more features of the data point? Should you use a decision tree instead of a linear regression? All of these decisions can be based just by comparing these two numbers, the training error and the validation error. And this is what I really want to see in your machine learning project reports. I want to see such a plot, training error and validation error, at least one such plot. Yeah, so there are now several questions, which is good because this slows me down. So there's one question. After validating the model, can we then train with the entire data set? So you use validation then. So first of all, you use validation to spot overfitting. So here on the right, we see a scenario where the training error, this blue bar is very small, but the orange bar is very large. So this means overfitting. And this means that degree 3 polynomials are not a good choice. And then in the next step, you can use this information to select between different models. So this I will talk about in a second. So then you can also look at the validation error for model 1, which is smaller. And you use then the validation error to choose the model. And after you have chosen the model, you might retrain it on the entire data set. But there are mixed opinions about this practice. I would say, just to be on the safe side, in the end, you should always look at the third data set, which is called the test set, which I will talk about later. But what you do before is kind of not always clear case. So it might be a good idea then, after you choose the model, to retrain it on the entire data set. Yes. Okay, there's another comment. So we should find a way to find the best balance according to training data points with the label or the next missing data point. Yeah, so as I understood the question, if I understood the question right, so you want to balance this training and validation error. So what you typically do not want is the training error is much smaller than the validation error. And you will learn different techniques like regularization or model selection techniques in this course that allows you to bring down. So what machine learning in practice is then about, try out different methods to bring down the validation error, even at the expense of increasing a bit the training error. And at some point they meet. At some point there's the sweet spot where they meet. And then you hopefully, what you get, this error here is acceptable. And if this error here is acceptable, for example, you have a target accuracy. You want to find the cat images with 99% accuracy, or you want to make the detection error smaller than 1%. And if this here is 1%, then this figure, then you're done. Then you have solved the problem. But in general, to start with, you will typically get a very small training error, but a large validation error, and then you want to balance those two. There's another question. In general, what percentage of data is better to be selected for validation? So this question addresses the choice of the split ratio. So here I choose 3 data points for training and 1 data point for validation. And the question is, wouldn't it be better to use 2 data points for validation and 2 for training? And I have to say there is no clear-cut answer for this. So there is no widely applicable rule or formula that tells you the optimal split ratio between validation and training. This depends highly on statistical properties of your data set. I will touch this a bit in more detail in round 4 of our course later on. Okay, then another question. Is it unusual to have smaller validation error than training error? Yeah, that's a very good question. So if the validation error is smaller than the training error, then this is a rather extraordinary case. And this might point to a wrong implementation of the training algorithm, because the training error is what you get on the data set on which you optimize your hypothesis. And it's somewhat unlikely that this error could ever be larger than the validation error that you then get on other data sets. It might be possible that you have pathological cases, Actually, that would be a good quiz question. If it could happen that you train properly, but the validation error is smaller than the training error. In general, this cannot happen, and this should not happen, let's say. And this would point at a wrong implementation of the machine learning algorithm. For example, there are certain parameters in the training algorithm, like a step size when you use gradient-based methods. So gradient-based methods are discussed in chapter 5 of my lecture books. And there are some parameters like a step size. And when this step size is chosen too large, for example, then the training doesn't work. It will never find the optimal hypothesis. And then you might end up with a training error that is larger than the validation error. So if the training error is larger than the validation error, this might be an indicator that something in the training algorithm is wrong. Yeah, that was also a very good question. Let me see, what other questions do we have? How to select training sets, how to select validation sets, any rules? In general, we just randomly select subsets. So you randomly divide the data set that you have into two subsets. One is used as the validation set and the other as training set. But of course, it might happen that you are very unlucky, in particular, if you have small data sets, that for some reason, the split is very untypical. So the validation set is a very, might be an outlier, for example. So it might not be representative for the whole data set. And then you might have an atypical behavior, let's say, of the training error. And to average this out, there's a slightly more fancy version of this simple validation method, which is called KFold cross-validation. And this amounts just repeat the validation step k times. K is a parameter. For example, k equal 5 is one popular choice. And no, I don't know a general formula for the optimal value of k also in this case. So this is often also trial and error. So you use different splits. So in each iteration, you use a different subset as the validation set and the rest as training set. And then you average the resulting training errors and validation errors over all these repetitions or folds. These are called folds for some reason. So this should avoid, or this should average out some unlucky splits, some very unlucky splits where the validation set would be really not representative of the entire data set. Yeah. Yeah, one comment. In KFold, do you change the training set each time as well, or just the validation set? Yes, because as soon as you change the validation set, you must also change the training set, because the training set is the complement of the validation set. Yes, so you change training and validation set in each fold. Another question, how many data points are required for validation? Yeah, there is no general rule. In general, you want what you use the validation set for, or what you use the validation error for, is an estimate or approximation of the average error that you get when you average all the prediction errors over all possible data points. In practice, you cannot do that, but what you could do is you could assume a probabilistic model, and then you can define a quantity called the risk, which is the expectation of the error. And the validation error serves as an estimate of this expectation. And then you can use tools from probability theory, which tells you how many data points do you need in the validation set, such that this estimate is within a certain percentage with 99% probability. So you get these confidence intervals. But these confidence intervals you can do only when you know a probabilistic model of the data set, and you need to estimate this probabilistic model. So it is possible, but it might not be really practical to get such formulas. But I have to say, this sounds like a good idea for a quiz question for round 4. Okay, how many data points are required for validation? I just discussed this. Yeah, so for this problem, when we look at this here, we have two models. Model 1, linear predictors. We got the training error and validation error. Then we did the same for model 2, degree 3 polynomial. So which one would you pick? Which model would you use? Model 1 or model 2? Model 1, yes, because the validation error is smaller. Yes, so you got already the idea of model selection. So you choose the model based on the smallest validation error. And we can interpret this validation error as the loss, something like a loss for a hypothesis space. So the loss which we used so far was used to measure the quality of an individual predictor or a hypothesis. So we used the loss to evaluate the quality of a single hypothesis. And the validation error is used to evaluate the quality of a whole hypothesis space or model. So it's a very similar idea, just it works on one higher level of this choosing between different models and using some measure to assess the quality of a model. Here we use a validation error to assess the quality of a hypothesis space, like the space of our linear predictors. And we can use this to say, okay, seems to be better than the space of degree 3 polynomials. So let's stick to degree 1 polynomials or linear predictors. Very good questions here. Let's see if I missed one. Yeah, then one question, how are the available data points partitioned into training and validation set? Yeah, as I said, we randomly select a subset as the training set and the rest is the validation set. And there I will then show in a few minutes, I will do a live demo where I show you with a few lines of Python code, which I cooked up half an hour before this lecture. And I'm not a pro in Python, I have to say. But they are so convenient libraries that all I talked about here, you can do in a few lines of Python code. Also this splitting into training and validation set. Okay. Yeah, so we now already discussed